Okay, welcome back everyone. So we are here in part 2, which is going to be the Python part, and this is a follow-up to my previous video about scaling. So if you didn't watch that, you might be a little bit lost, and you would probably want to watch that one first. If you remember in the video about scaling, we found a good values of like a ballpark estimate for what the molar flux of acetone and methanol would be. And we also found these two Stefan-Maxwell equations that we're going to need to solve. And these are simultaneous differential equations, and it's going to be an initial value problem for us to solve. Okay, so to start out this coding, I'm going to import a library of functions called numpy. I'm going to call that np just because it's easier to, it saves time typing np instead of numpy a little bit of time. I'm going to import a few functions from SciPy, which is another library of functions. I'm going to import solve IDP, which is going to solve our initial value problem, which is going to be those Stefan-Maxwell equations. And then I'm going to also import root. And that's going to get our roots for when after we solve the differential equations, we're going to need values for molar flux of acetone and methanol to where the value of the mole fractions at delta is going to be 0. And at the end of this, we're actually going to be making some graphs to plot the mole fractions along the z-axis from 0 to delta. And to do that, we're going to import some functions from Plotly, which is just a library of functions that we're going to use to make some plots, or our graph. So I'm going to import make subplots. And then I'm also going to import graph objects. As geo. And again, importing this as geo, it'll be easier to just type geo rather than graph objects when we use it later. So this is all we're going to import. Now what we need to do is we actually need to go through here and plug, just give our variables values. So first thing we are going to do is our Stefan-Maxwell coefficients of diffusion, 8.48. $13.72. And the reason why we have to go through and type all this in is because we're going to be using all these numbers in calculations within our code. So we have to make sure these are all input. We're going to put in our pressure, which is 99.4 kilopascals. So that's going to be 99.4 times 10 to the third pascals. Yes. And then we're going to do our temperature, which is 328.5 Kelvin. We're going to be using concentration, as you can see down here in our Stefan-Maxwell equation. So we know that concentration equals pressure divided by the gas constant times temperature. And actually, I'm going to go ahead and put in our gas constant, which is 8.314. And then we have delta, which equals 0.24 meters. Now, actually what I'm going to do here is I'm going to define some variables for myself and I'm going to call it F12. And what this is going to be is it is going to be this right here. It's going to be concentration times the Stefan-Maxwell coefficient divided by delta. And this is just going to kind of condense the amount of variables that we're actually going to be typing in. It'll make things a little simpler. So it's going to be concentration times the Stefan-Maxwell coefficient between 1 and 2 divided by delta. We're going to do the same thing for 1 and 3. And then finally, we have concentration 2, 3 divided by delta. Okay. So now what we want is we're going to put in our initial values for the mole fraction of acetone and methanol. So we'll call this Y1 initial equals 0.319, and we have Y2 initial equals 0.528. Okay, and then last but not least, we're going to have our guesses for N1 and N2, molar flux of acetone and methanol, and I'm going to call this N1G for N1 guess. And remember, we said that that's 10 to the negative third. And we have N2G, it's going to be negative third. Okay. So this is going to be all the information that we need to solve this. So now I'm going to go down here, and I am going to use this called solve IVP. And I actually have this pulled up over here. This thing that popped up right here. This explains all of the parameters that we can put in. I have this pulled up over here because it's a little bit easier to read. So we're going to need a few things. First thing is fun. And let me be clear, this is not happiness. It means function, which is kind of the opposite of happiness, really. We're going to need that. We're going to need this t underscore span, which is going to be our interval of integration. Now, this would be 0 to 0.24 because delta is 0.24, but we scaled our problem to be between 0 and 1. So this t underscore span, this interval of integration, is actually just going to be 0 to 1. Now, we have our y naught, which is our initial mole fractions. We're going to have method. These are just different methods to actually solving the initial value problem. And then finally, we have dense output, and we're going to set this equal to true. And it'll bring up some information that will help us. So that's why we're going to set it to true. So first thing is this function that we need. It needs to look like this, t and y, where t is a scalar and y is an array. So, and it's going to be our dependent and independent variables. So we need to define a function. I'm going to call it dy, and it's going to be our independent variable is eta, and our dependent variable is y, and this is going to be an array. Y is an array. So the way Python handles arrays is that the first number in an array is index 0. So for 3 values in an array, it would be 0, 1, 2, rather than 1, 2, 3. So to make things simpler for myself, I'm going to say the y1, which is the mole fraction of acetone, equals the first number in the array. And y0 means the first number in the array because index starts at 0. Then y2 equals the second number in that array. So that's y bracket 1 for the index 1 in the array. And then finally we have y3, and just from the definition of mole fraction, we can say y1, 1 minus y1 minus y2. And what we want to do is we want to return an array that's going to be our Stefan-Maxwell equations. So we're going to make an array, and it's going to be our Stefan-Maxwell equations. So I'm going to go ahead and type these in. It's going to be y1. So y1, this, it's going to be in a, well, let me say this. There's going to be two parts. There's going to be two values in the array. The first one is the first Stefan-Maxwell equation. The second one is the second Stefan-Maxwell equation. And you want to be careful when you're typing this in because you can get some errors here. Now right here is actually where these F12s come in handy. F12, F13, F23. It just saves us a little bit of typing. And then actually I want to peek over here real quick. Minus y3 so we have y3 times n1 divided by, this is going to be f13. Okay, and then for the second expression in this array, we're going to have y2 minus y1 and 2 divided by f12 times n times n2, 2, right, divided by f23. Now, actually something I realized here is that we actually want to run this with our guesses. So I'm going to say n1g, n2g, n1g, n1g, n2g, n2g. Okay. And okay, so that's going to be our function. It's going to the equation with the guesses put in, our two Stefan-Maxwell equations. So now we're going to use solve IVP. So first we're going to do our function, which is dy. Then we're going to do our interval of integration. So that's going to be 0 to 1. Then we're going to put in our initial values, which is going to be y1 initial and y2 initial. And then method. So for method here, there's quite a few different methods here: RK45, RK23, Rado, BDF. And this is just the method to actually solving the initial value problem. I'm going to be using Rado, but tell me down in the comments below which method is your favorite. I'm sure I'd love to try some of these sometime. Some of them seem pretty cool. Like BDF, that's probably pretty cool. So yeah, I'm gonna be using Rado though. But yeah, tell me all about your favorite method in the comments. I'm using Rado because it's the best. Don't ask me why, because it just is. So we'll do Rado. And then we're gonna set dense output equal to true. Okay. So run this. Hopefully no errors. Hopefully no errors. We've had errors in the past. Okay, so this is telling us it worked. Now this right here, SOL, this is actually kind of where the answer that we're looking for actually lies. So what we're gonna do is we're gonna set this as a variable equal to the result, and then we're going to result dot SOL, which is this SOL down here, Now, whatever value we put in here for our independent variable, it's going to solve the equation, solve the differential equations, and it's going to tell us what the mole fractions are at that independent variable. So, for example, I want to say SOL1. And it's going to return an array here. So what this means is that for when our independent variable is 1, the mole fraction of acetone is this, and the mole fraction of methanol is this. Now, this is an issue because our problem is scaled to be from 0 to 1. So 1 is at the very end when z equals delta. And we know from the problem that the mole fraction is 100% air at that point, which means that the mole fraction of acetone and methanol should be 0. These are not 0. That means that our guess is wrong. Our guess for N1 and N2 is wrong. So now what we're going to do is we are going to set up a root solver to find what values of N1 and N2 will make this be 0. So we'll do root. Now for root, not sure why I need to do root. Usually stuff, am I calling this wrong? Root. Did I input it? Oh. Root. There we go. Lowercase r. So we're going to do a function. Again, this is not happiness, this is functions. Not happy. And then our initial guess. So this is kind of where our initial guesses come in handy, of 1 times 10 to the negative third. So what we need to do, actually, is we need to set up something up here. We need to find a new function. Function of n. Oops. Did not need to run that. And this n is going to be our variables for the actual molar fluxes, not our gas. So this is what our root function is going to be trying to optimize in order to make the differential equation equal 0 at delta. So this is an array, n is an array. So what we need is, we're going to do the same thing we did for the array of y. We'll call n1 equal to the 0th index of the array. This is just to make things easier for me. Okay. We're going to return this. So we're going to do f, and then we're going to do n1g and 2g for our 2 guesses. We're going to run this. Well, hopefully it works. Okay. And we get an array back, and it's going to be under x. So that is where our that doesn't seem right. Huh. Aha. This should not be guess anymore. We are actually solving the initial value problem. We're solving the Stefan-Maxwell equations with the actual numbers, not the guesses. So run this again. Okay, this looks a lot better. So this tells us that for these values of the molar flux of acetone and methanol, those are going to be our correct values. So we'll call this res for result. Now what we want is we actually want to be able to get to those values. So I'm going to define two new n1 and n2s. And this is going to be res.x1. Is that right? 0.003. Yes, 0.003. Okay. Just checking to make sure I have the right notation here. So this is going to be n1, and n2 equals res dot. It's going to be the second value in that array. Oh, and I actually just fell for the Python trap. We have to remember that when we're talking about an array, the first number is the 0th index, and the second number is the index 1. Yeah, it almost got me. It almost did, but not today. So now that we know these values, what we're actually going to do is just run the, we're just going to do the equation again. I'm actually just going to copy this down. Okay, we don't need that. Run, make sure it runs. Okay, we have some indentation problems. Fix that real quick. Okay, try it again. Okay, it seems to work. So yes. So right now we just solve the differential equations with the correct numbers. So actually I will demonstrate. If we do result.sol, this is from before, this will tell us, I'm going to do 1. This will tell us what the mole fraction values are for when eta equals 1. We get negative 3 times 10 to the negative 13th. So we're expecting 0. This is not 0, but this is basically 0. It's probably due to a rounding error from the computer, but this is kind of what we're looking for here. And if we put in something like 0.2, it'll tell us what the mole fractions are at 0.2. So what we want is we want to plot all of these onto a graph. We want to plot how the mole fraction of acetone changes, methanol changes, and air changes as we move from 0 to 1, or 0 to delta. Now in order to do that, I'm going to set up an array. So I'm going to call it eta plot, and we're going to do this np.space. This is just going to make an array of numbers from 0 to 1, and it's going to be 51 equal intervals. So if we look at this, this is going to be what it looks like. It's just 0 to 1 and 51 equal intervals. And now what we're going to do is we're going to do we are going to do result.sol. And like before, this is going to take different values for eta, and it's going to tell us what the mole fractions are at that point. Eta plot. Okay, so this is what we get. we get the mole fractions of acetone at each point in eta plot. And remember, eta plot is from 0 to 1, and it's 51 equal intervals. So it tells us what the mole fractions are at all those intervals. So this is 50 intervals, 51. And then we get methanol over here. Okay. So now we're going to graph this. Because this is actually we're almost done. This is really the information we're looking for. We just need to visualize this, because this is ugly. Yeah, this is horrendous. So what we're going to do is we're going to make a plot, and we're going to use make subplot. This we did this up above. Import make subplots. And I think we're going to do rows equal 1, columns equal 1. Okay, and then we're going to do figure dot add trace. This is going to add a line. Graph objects, which we imported before. Let's scatter. We have x equals eta. X equals eta plot. Yep. And we have y equals so y is going to be these numbers here. So what I'm going to do, I'm just going to call this I'm going to call this y. And we want the first index for the 0th index in this array, this y array. So y equals y, and it's going to be 0. Okay, and then we're going to name it acetone. We're going to run it. Hope it runs. Make subplots. Okay. Aha, this should be capital. There we go. So this is our acetone. And it starts at about 0.319 and it goes down to 0. And that's looking good. That's looking really good, actually. So we're going to need to do this for methanol and air. So I'm going to do some caveman coding here and copy and paste, because I can. And we're just going to change this to 1. And this is going to be methanol. This is going to be air. And we don't actually have a spot in our, we don't actually have values for air. But the way mole fractions work is that air equals 1 minus acetone, minus the mole fraction of acetone, minus the mole fraction of methanol. So I'll go ahead and do that. And here's our plot. So we have air in the green, which starts down here and goes up to 1. And we have acetone and methanol, which go down to 0. Now this is between 0 and 1, because we scaled our problem to be between 0 and 1. So on our x-axis here, this is actually eta. Now I'm going to go ahead and change this to z. So what we can actually do is multiply by delta. We're kind of unscaling it right now. Delta, run this again. And now we're 0 to 0.24. So this is the graph of the of the mole fractions from z equals 0 to z equals delta. Okay, so we are done here. Thank you for joining me for this very cool problem. Some cool Python coding and Google Colaboratory. It's actually really cool. I didn't know this existed. This is actually really cool. It's just free Python. It's really handy actually. But yeah, so we're all done here. Thanks for watching, and I will see you in the next problem.